Hello students, this is Advanced IC Engines, subject code AU407. In this class, I will give introduction to the subject and we will see few animations which is related to Wankel engine, Stirling engine and free piston engine. Okay, so in first module, it has 6 module. In the first module, types of engines will be discussed. Basically, here Wankel engine, Stirling engine, free piston engine, light duty diesel engine, high pressure pump technology, multiple injection diesel combustion. These working principles will be detailedly discussed in the first module. Okay. Before we study about Wankel engine, I will just tell about the types of engines, IC engines. Basically, we can classify the IC engine into ஆமா basically engine is classified as internal combustion engine and external combustion engine. Here we are going to see the classification of internal combustion engine. In many ways we can classify internal combustion engine based on the application. Okay, based on the application, automotive IC engine, locomotive, light aircraft, power generation, agriculture, earth moving, home usage. Based on the applications we can classify like this. Okay, further, automotive, if you take automotive means car engine, bus, highway, off highway engines. Okay, the vehicle which will be used in off highway, those engines. So here you can see some engine models. So this is about fact about 14 cylinder version. It's a huge engine. Total engine weight is 2300 tons. Okay. Another classification based on the engine design. Reciprocatory engine and rotary engine. Okay, reciprocatory engine and rotary engine. Rotary engine means local Wankel engine, and those engines are called as rotary engines. Okay, best example is Wankel engine. Reciprocatory engine means in basic, in even in bikes we can see. Okay, it might be a single cylinder 4-stroke engine or 2-cylinder 4-stroke engine you could see in bike. Okay, if you take cars, bus means there will be like 4-cylinder, 6-cylinder, like that they are using. Okay, so single cylinder, multi-cylinder. Further, if you take multi-cylinder means arrangement of cylinder based on the arrangement of cylinder, inline cylinder, V cylinder, radial, opposed cylinder, opposed piston. Okay, like this we can classify the multi-cylinder. For the rotary engine is classified as single rotor, multi-rotor. Okay, so these are the models for inline engine, V V engine, horizontally opposed engine. Okay, opposed piston engine, radial engine. So V engine model. So this is the example of Wankel engine. Later I will show the animation of Wankel engine. In the earlier classes we have studied about 2-stroke and 4-stroke engine, the working principle of 2-stroke and 4-stroke engine. Now we are going to study about Wankel engine.
Parts of Wankel engine or rotary type engine. It consists of casing, cylinder, 3-lobed rotor or rotating piston, stationary gear, spark plug, water jackets, inlet port and exhaust port. Let's talk about some interesting features of Wankel engine which makes it different from other types of engines. The 3-lobe rotor rotates eccentrically in an oval-shaped chamber, mounted on the crankshaft through external and internal gears. The internal or pinion is fixed in the casing over which the rotor rotates about its own axis, and at the same time it rotates about an axis of the fixed gear. In Wankel engines, in one revolution of the rotor, there are 3 power cycles. As compared to the 2-stroke engines, Wankel engine produces 3 times more power, and as compared to 4-stroke engines, they produces 6 times more power. Working principle of Wankel engine. The Wankel engine works under the same principle as 4-stroke Otto cycle. That is, all the 4 processes, suction, compression, power and exhaust, are performed by the eccentric rotor by the lobes ABC as shown in the animation. Let's talk about these strokes one by one. First stroke, induction or suction stroke. As the tip of the rotor passes the inlet port clockwise, the petroleum mixture enters the chamber, which increases in size because of the rotor's eccentric orbit as shown in the animation. Second stroke, compression stroke. As the rotor continues to revolve, the chamber containing the mixture decreases in size and the mixture is compressed. Third stroke, power stroke. Ignition causes the mixture to burn and expand, imparting energy to the rotor for its power stroke. As a result, the size of the chamber increases as shown in the animation. Fourth stroke, exhaust stroke. The leading lobe passes the exhaust port and leaves it open for the gases to escape till lobe back to it covers the exhaust port. Thanks for watching, friends. Please don't forget to like our video and subscribe our channel, and also press the bell icon so that you will be notified whenever we upload a new video.
This is our gas box. The same Stirling engine is sitting in the solar solution, the CSP solution. The basic principle of the Stirling engine is that you have a working gas. This working gas you heat up and you cool down. By doing so, you expand it and contract it. When the gas is heated up, it expands, thereby pushing down the piston. and the next cycle is being cooled down and piston goes back. The cycle is that you heat up, cool down the working gas about 25 times per second to 700 degrees and 80 degrees. And this is the basic of the engine. And the similarity of a car engine is that you actually have a crankshaft here. This crankshaft is directly connected to a generator, thereby producing electricity with, in the solar solution, no emissions whatsoever, and on the CHP solution with very small emission.
But free piston engine is a sort of two-stroke engine having no crankshaft. Now how work is done then? Means what is the utility of this engine? In case there is no crankshaft, what is the utility? The utility is that the power is obtained by expanding the exhaust gases coming out of the two-stroke engine in a gas turbine. Okay. So once again, that free piston engine is basically a two-stroke engine which is having no crankshaft, and the power is obtained by whatever exhaust gases are coming out of the two-stroke engine, and those exhaust gases are expanded in a turbine. So let's understand how it works. First of all, we will learn that what are the basic components of free piston engine. This is the principal diagram. It consists of a bound cylinder, as I am showing by the help of arrow. This is bound cylinder which is having a piston with it. So bound cylinder is nothing but it consists some air trapped in between the piston, this piston and the cylinder. So in case that air is compressed by the piston, then it stores the energy, whatever energy is given by piston to the air, it stores the energy in form of pressure energy of air, because this bound cylinder contains air. So in case air is pressed inside, so it acts as a spring, so it stores whatever energy is delivered by this bound cylinder piston to the air. So once again I will like to tell that this is the bound cylinder and this is the piston of bound cylinder. So this piston can compress the air which is trapped between the bound cylinder and the piston. So in case the work is done over the air, so whatever energy is supplied by this piston to that air, it is stored in form of pressure energy of air. Now this is another piston. This is the see, if you divide this entire system in two parts, then one is this right hand side is the bound cylinder part, and this left hand side is actually the two-stroke engine. This is the gas turbine which runs by the help of exhaust of two-stroke engine. So by the help of arrow I am showing the boundary that this system is actually the two-stroke engine, and this system is the bound cylinder. So it consists of two main parts. One is the bound cylinder, other is the two-stroke engine. Now this is the piston of two-stroke engine, and we know this thing that in two-stroke engine there are ports. So this is the inlet port of two-stroke engine, this is the exhaust port, and there is a spark plug you can see. And what happens that the connecting rod of this piston is connected to the piston of this bound cylinder. This piston is the piston of two-stroke engine, but the connecting rod of this piston is connected to the bound cylinder piston. So in case this piston moves to and fro, means right and left, then as the piston executes motion to and fro, the same motion will be executed by this bound cylinder piston also. This piston is meant for two-stroke engine side, and this piston is meant for bound cylinder side. Okay. Now this is, by the help of arrow I am showing, this valve is a non-return valve which is ultimately connected to a duct. That duct is ultimately connected to a carburetor. So what is the job of carburetor? Carburetor makes the mixture of air and fuel, and of course in case we are talking about petrol engine, then fuel is petrol in that case. Okay. Now this duct, you can see this this inlet port is connected by the help of duct behind this piston. You can see that this is the entire cylinder, this is the piston. Behind this piston, this inlet port is connected by the help of duct, and this system is closed system, means the piston is connected to this connecting rod and to this bound cylinder piston, but it moves inside this cylinder to and fro, but this system is perfectly sealed. I am showing by the help of arrow, no air or fluid can pass out or leak out from this two-stroke engine side system toward the outer environment. It is like this. So once I will tell you how it operates, you will easily understand. Okay. Now imagine that this bounce cylinder is having some pressurized air inside it. This I am showing the pressurized air by the help of this red color, and toward this two-stroke engine piston, over its face inside this cylinder or combustion chamber, there is some air fuel mixture. So once again, imagine that initially I was just showing the diagram, the principal diagram. Now imagine this bounce cylinder piston is containing some pressurized air with it, and toward the left hand side of this piston of this two-stroke engine, there is some charge. It is like this. So pressurized air and charge. So in case over here in the bounce cylinder there is pressurized air, so what it will do, it will push this piston or not. This bounce cylinder piston will be pushed toward left hand side. So what will happen, when it will push toward left hand side, then this piston will compress the charge inside the cylinder or not. Yes. See, initially what was the case, the bounce cylinder was containing pressurized air, and toward the left hand side of piston there is charge. Okay. Now in case this piston is allowed to move, then this pressurized air of bounce cylinder will make it to push toward the left hand side. So whatever charge is contained over this left hand side cylinder, that is the combustion chamber, will be compressed by this piston. But one thing more will happen. Since this piston is moving toward left hand side, so what it is doing, since this piston is moving toward left hand side, so what it is doing, when it is moving toward left hand side, at the same time it is creating a vacuum behind. You can see over this system, the system behind this piston will have vacuum, because here the volume is increasing, here the volume is decreasing, but here the volume is increasing. So the system volume is increasing, so a vacuum will be created. So what will happen, this is a non-return valve. Okay, so it will open inside, and from the carburetor some amount of charge will enter behind this piston of two-stroke engine. So it is like this. You can see this valve has lift up, and some charge is sucked inside behind this two-stroke engine piston, and toward the left hand side whatever charge contained previously is compressed. Now when it is fully compressed, a spark is introduced by this spark plug, this blue colored spark. Now what will happen, this entire air fuel mixture will be ignited. So what will happen, now here the pressure is raised. Okay, so it will push the piston toward right hand side now. Okay, so what will happen, now the piston will move toward right hand side. So when it is moving, you can see, so when it is moving toward right hand side, what will happen, see, this valve is a non-return valve. So when the piston is moving side of this two-stroke engine piston, there is fresh charge. Okay, and bounce cylinder is containing pressurized air. So again this bounce cylinder piston will push this piston toward left hand side. Again it will be compressed. Okay, then again spark is developed in the spark plug. This fluid will ignite, again piston. And one thing, that when the bounce cylinder piston is pushing this piston, then at the same time behind this two-stroke engine piston the charge is sucked inside from this carburetor through this non-return valve, and when it is moving toward right hand side, spark is developed, and this piston is pushed toward right hand side. Again the charge behind this piston is compressing. It is having only one way through which it can go out, that is through this inlet port via this transfer duct, but piston itself is acting as a blockage. This compressing charge behind this piston is only having one way to escape, that is through this transfer duct through this inlet port. But what we can see, that piston itself is a sort of blockage in this inlet port or not. Yes, see, whatever charge is compressed behind this piston can come out through this inlet port, which is connected by a transfer port, because this non-return valve doesn't allows the charge to go back, but this piston itself is closing this inlet port as well as this exhaust port. It's like this. Now what will happen, with further expansion of these burned gases, which are over the left hand side of this piston, ultimately when piston removes itself between the way of outlet port and inlet port, what will happen? Two things will happen simultaneously. Those are, whatever the burnt gases over here are will go out from this outlet port and reach to this gas turbine. So since these gases are still hot, so these hot gases will expand in this gas turbine, so work is developed in the gas turbine. Second thing is, since from the inlet port piston has removed itself, so this pressurized charge which is contained behind this piston will get its way to enter inside the cylinder. So two things are happening simultaneously. Those are, the exhaust gases are going out through this outlet port, reaching a gas turbine, and whatever the fresh charge is there which is compressed behind this piston will get its way open inside this combustion chamber. And the third thing is, bound cylinder air is now fully compressed, means whatever energy is delivered by this piston to this bound cylinder piston is converted into pressure energy of air. Now again the system has reached to its initial state, that is the bound cylinder is containing pressurized air, and over the left hand side of this two-stroke engine piston there is fresh charge. So what will happen? This bound cylinder compressed air will push this piston of bound cylinder toward left hand side. So whatever charge is contained inside this combustion chamber will be compressed by this piston, and at the same time from this non-return valve through this carburetor fresh charge is sucked behind this two-stroke engine piston. So ultimately spark is introduced in this combustion chamber. So this fuel will ignite, it will again push the piston toward right hand side. At the same time behind this two-stroke engine piston, whatever charge is sucked inside, since this is non-return valve, will start compressing, as well as whatever energy which is supplied to this two-stroke engine piston is also supplied to this bound cylinder piston. So when the piston is moving toward right hand side, then it is compressing the charge is contained behind this piston of two-stroke engine, as well as the air contained inside the bound cylinder is also compressing by the help of the piston of bound cylinder. So whatever charge which is behind this two-stroke engine piston is having only one way to go out, that is through this inlet port inside this combustion chamber and via this transfer duct. So ultimately the same condition will come, that piston will remove itself from the way of inlet port, whatever fresh charge is there will go inside, and the burned gas will come outside through this outlet port. It will in turn run a gas turbine. So like this the cycle completes. So what we see over here, that actually whatever work is done over the piston, that work is transferred to compress the air of bound cylinder. So actual energy for utilization is developed in a gas turbine, and by the help of what? By the help of whatever exhaust gas coming out from this two-stroke engine cylinder. So hope you would have understood what is a free piston engine. Remember, free piston engine is principally a two-stroke engine which is having no crankshaft, and we want power from engine. So how that power is obtained? Since there is no crankshaft, whatever the exhaust gas is coming out from the two-stroke engine, those are expended in a gas turbine to get power. Thank you.
Conventional diesel engines are characterized by an orange-colored flame because they do not achieve complete combustion. This results in unburned soot that is emitted as black smoke. Attempts to reduce soot by improving combustion characteristics, however, have increased the combustion temperature, resulting in higher NOx emissions. This trade-off between NOx and black smoke has been a major dilemma of conventional combustion systems. MFire Combustion is a totally new combustion concept that transcends the limitations of conventional systems to achieve a blue, clean flame for the first time ever in a diesel engine. As a result, it succeeds in reducing both black smoke and NOx simultaneously. How does MFire Combustion differ from the combustion process in previous diesel engines. MFire Combustion incorporates 3 revolutionary technologies that overturn previously held ideas about diesel engines. These technologies are the formation of strong swirl, the application of heavy exhaust gas recirculation, or EGR, and optimization of the fuel injection timing. A newly developed helical intake port is used to generate stronger than ever swirl motion in the air in the cylinder. The fuel spray is injected under high pressure into this strongly swirling air, enabling the fuel and the air to be thoroughly mixed. After being mixed with the air and thoroughly evaporated, the fuel is completely burned. This produces a blue transparent flame, and virtually no unburned soot is formed. Recirculating a large quantity of exhaust gas to the intake air keeps the combustion temperature from rising, because the density of oxygen is lowered. This makes it possible to reduce NOx that previously formed under high temperature combustion. Moreover, the fuel injection timing has been optimized by considerably retarding the injection of fuel compared with existing diesel engines. This completely new approach moderates the combustion process, so that combustion noise and engine vibration are greatly reduced. The formation of strong swirl, the application of heavy EGR, and optimization of the fuel injection timing. These 3 revolutionary technologies transcend the traditional notions of diesel engines to achieve simultaneous reductions in black smoke and NOx, which was previously regarded as being virtually impossible. Let's take another look at the differences between conventional combustion and MFire combustion. In the conventional combustion process, combustion begins when the piston is at the highest point in the cylinder. The resulting high pressure and high temperature combustion produces noise and NOx. In addition, the remaining fuel is not fully burned in the latter half of the combustion process, resulting in the formation of soot. With MFire combustion, on the other hand, the fuel injection timing is optimized, and heavy EGR is also applied to control the combustion temperature, so as to inhibit the formation of NOx. And because the fuel and air are thoroughly mixed by the strong swirl motion in the cylinder, the mixture is burned with a blue flame that is not conducive to soot formation. MFire combustion also begins more moderately than conventional combustion, which has the effect of keeping noise and vibration low. In short, MFire combustion achieves a blue clean flame to substantially reduce NOx emissions, black smoke and noise, the drawbacks of existing diesels, while maintaining the excellent fuel economy and high output of direct injection diesel engines. Nissan's MFire combustion concept represents a breakthrough technology that overturns traditional ideas about diesel engines.
Supply fuel system. So we're going to go through the very basics. As modern systems develop, each system varies and improves and changes. So there's going to be lots of, generally speaking, when it comes to these systems, but I'll do my best as I go through. So to start with the basics, we have a fuel pump here and a fuel pump here. This is direct injection, high pressure fuel pump. This is still high pressure, but in comparison to this, a low pressure diesel injection pump. They're both driven by a main shaft that goes in, which is usually turned by the cam belt. Later systems have been turned by the camshaft. The initial differences is this runs to a couple of 100 bar pressure, and these latest systems, these run into the thousands of bars of pressure. A fuel pump like this could easily produce 1800, 1700-ish a bar of fuel pressure at the fuel rail. So there's the first rather large difference. The second main difference between these two fuel pumps is this one just simply creates a pressure. It doesn't actually determine when each injector fires. However, this fuel pump, an early Bosch fuel pump that runs on XUDs, etc., well, this determines also the point at which each injector fires by the delivery valves that are on the end. So, on the end of the injection pump, there's 4 delivery valves on this one, so it's a 4-cylinder engine. Some are 6, and that would obviously be a 6-cylinder engine. And each of these delivery valves runs via a pipe to one of the injectors. And as the shaft inside rotates, not only do the vanes inside create the pressure it requires, but they also deliver fuel via the head, via a shaft in here, to each valve as it rotates, as you can imagine, and then each one goes to each cylinder and creates the firing order. As opposed to our direct injection here, which simply has basically just one output. This output goes to a point on the fuel rail, which happens to be on here on this fuel rail. And then, because this is a 4-cylinder, you have 4 outputs from the fuel rail that then go to each injector. So this injector rail, although it doesn't look much, this holds, this holds all the fuel pressure. So whether that be 1,000 or 1,500 or 2,000 bar or more on modern systems, which is why we get some systems like this called the common rail injection. Now, older systems also had common rail, we're talking old systems, but often when we speak of common rail, we're talking about these modern fuel injection systems, these modern diesels. So there's the initial differences. So we've got pressure, the way the timing is done, so each time the fuel injector fires, and then we go on to the injectors. Now this is where the differences again in control happen. So while an ECU is required to control all this, some of these systems later on had ECUs, hence there's a little sensor on the top, but generally speaking these were completely mechanical. For instance, inside one of the top of this is one of these, which is the governor and the throttle, and there's a bunch of springs you can see which control everything. So in comparison to ECU control, it's all about springs, and you can modify these little things for them to rev harder. So it's just all about nuts and bolts, as opposed to this where it's on the laptops. But of course there are some advantages and disadvantages. You see these are much more expensive, they require a better filtering system, and for instance all this stuff that I have out here really is kind of useless until I put it into an ultrasonic cleaner because it's all exposed to dirt, as opposed to these which will kind of run on almost anything. When we get to the injectors, you'll notice quite a stark difference. Again, in size, this is actually quite a simple injector, really, and a simple system. It has a needle point injector there, and inside is a spring or 2-rate spring, and as the fuel pressure reaches a certain point when it gets to this injector, it opens, releases the seat, and the injector fires the fuel. Because these are indirect injection, the head design is also different. So these fuel injectors sit, and this little point here sits right onto the top of the cylinder, so as the cylinder comes up, it fires onto the cylinder. Hence the pistons are often different on the direct injection as the indirect injection. Indirect injection, the piston comes up and it's got a flat head to it. And a direct injection system, well, that's a little bit different. Let me show you what happens when it goes wrong. So we have a valve in the middle of ours, that's from the lemon, but you can see there's a bowl in the middle which helps create a swirl effect to help the fuel and the air mix. As opposed to the XUDs, the old designs, the old heads, the indirect injection, well, they had a little port, a little bit like that bowl, inside the head with a little gap. So as the piston came up to the head, all the air swirled inside, it injected into the sort of swirling chamber, the swirl pot, and then came back out and exploded, bang, pop, wallop, and your piston went out the side of the engine. So these modern injectors, as you can see, they have a plug on the top, and it's the ECU that fires each one. So there's a common amount of pressure that's supplied to each of the injectors, and the idea is the ECU knows exactly when to fire each injector and for how long, whereas that's all determined by springs inside the pump. Which of these is better? Well, it's time for a brew to think about that. There's many ways we could weigh up this question, and there's going to be lots of heated arguments, perhaps in the comment section about this. There's already been many heated arguments over the years since these new systems came out. When we're talking about indirect injection, there's not many arguments that Lucas make a fuel pump that could be run on the same engines, and they are not as good. These are far superior for a number of reasons. The tunability, the general reliability, although there are many Lucas pumps doing hundreds of thousands of miles, and also the fact that you can run these pumps on many different things. So, for instance, you could run it on vegetable oil or many different diesels. You could even run it on an engine oil. I've heard all sorts of fuels be run through these pumps, and they do, well, just fine. Sometimes a little seal here goes, but generally speaking, you can basically just chuck some chip fat in them, and you can run away and drive quite happily along, smelling like the local chip shop, but very cheap on fuel. So many people do that. You couldn't do that with these modern systems. You could for a short while, but no doubt some part of this very sensitive system would fail. However, is this system better? Well, yes. It's more modern. And whilst a lot of modern things, we like the nostalgia of the old things, it is superior. It creates higher fuel pressures, which enable you to run more power without stresses and strains on springs and levers. And there's more flexibility with the tuning process. So you can fire more fuel in this system in a shorter period of time, which is obviously better for combustion and atomization of the fuel. However, of course, if you just like playing with springs and spanners, you don't like laptops, well, this is the system for you. But it is dying out because parts are dying out, cars are dying out, so parts are getting a little more difficult to get hold of. Parts are more expensive with these systems, but generally if the system is looked after, it is plenty reliable. And if you prefer laptops rather than getting your hands dirty, well, this is the system for you. Remaps can be had, you can download them, plug them into your car, and suddenly you have 50% more torque and 20% more power just from a remap because of the potential of these direct fuel injection systems. Which is why now modern petrols have gone the same way with high pressure direct injection fuel systems. And if you check out my project up here, Kev, we're using an old Mini and we're going to put a modern engine in it with direct fuel injection, just because this is the way basically technology is moving. I don't want to bore you too much. I still love the old system, the indirect injection systems. It's how I started my apprenticeship. I've had many cars on this, and maybe one day I'll end up with another one again. But for now, I'm moving ahead with the times with modern fuel injection. I've seen the benefits, I've felt the benefits in my gut when I put my foot down. Generally speaking, it's the future. And sometimes we just have to go with it. We like the nostalgia of the old things, and we like the fact we can run chip fat, but until the need to do that again, I'll be with this system. Now, I spoke very generally about facts and figures that are general, so please don't slate me if you know other things about this. If you do, well, put them in the comments. We're all here to learn. Every day's a school day. But I've been asked many times what the basic differences are and which is best. Well, you can argue all day about those facts. In my personal opinion, the more modern systems are better. However, they do have their issues at times. Generally speaking, the repair factor is more costly. But that's getting better as companies and people start businesses rebuilding such systems as this rather than replacing it for new pumps. Thousands of pounds, a rebuild, 300 quid, for instance. So kudos to them, and I thank them for doing such things, those people investing in kit to do those things, and we applaud them and hope that happens more often. Of course, it all can still go wrong. Check out my lemon project, and things can blow up. Ironically, that was mechanical. So thanks for watching to this point. I hope I haven't bored you too much, but please check out Piggy Pal, the other videos. Sometimes I have frequently asked questions that I answer, so why don't you ask a question and I'll see if I can answer it with another factual video. Usually I'm just spannering and doing stuff on daily cars and making stuff go faster, so please check out those videos too. Any suggestions welcome, any comments welcome. Keep them polite and kind and don't swear. Thank you. Piggy out.
Let's look at the internal workings of the high pressure fuel pump. Here we can see everything labeled. As we look to the right side, we can see a demand control valve. Now that's just one manufacturer's name. Sometimes it's called the fuel volume control, fuel pressure control. No matter what it's called, it is a simple solenoid, and it controls how much fuel from the low fuel pressure system is delivered to the internal workings of the high pressure pump. At the bottom we can see that special cam lobe on the camshaft. Now there's two strokes. It's a simple piston that goes up and down. There's a suction stroke and a pressure stroke. All of this is controlled by that cam lobe. During the suction stroke, the piston falls to the bottom, and what we have is fuel being drawn into that chamber. Then the pressure stroke is driven by the camshaft lobe, so the piston comes up and pressurizes that fuel in the chamber. And there is a pressure relief valve to keep this pump from internal damage, and that's set by each manufacturer. The fuel pressure is going to be controlled by how much volume the fuel volume regulator or the fuel pressure regulator, that simple solenoid, allows into the high pressure pump. When it's de-energized, it opens the fuel inlet internal to the pump, and then the fuel flows into that pumping chamber where the piston is at the bottom of its stroke because the eccentric is pointing down on the camshaft. Then when the camshaft forces the piston back up, then the piston travels upward to the top of the eccentric, and then that fuel is compressed. It has to overcome the outlet valve spring, and then the high pressure fuel is now delivered to the common rails. The fuel pressure, once again, is controlled by how much volume through the pump. When we talk about the GDI injectors, we say that there are very small injector pulse width openings, 5 to 7 milliseconds. It's not a wide range like PFI. What controls the injector fuel flow is the fact that the computer is controlling a solenoid out on the high pressure pump, and it controls it by how much fuel it allows into the high pressure pump.